imagine some people will be filing in, but I'm going to go ahead and get started because this is actually a one-day workshop that we tried to compress into 2 hours, so we appreciate you bearing with us. My name is Cedric Hurst. I'm with a company called Spantry. We're a merry band of engineers and DevOps people and non-technical people. We're based out of Chicago. We do a lot of solutions for a lot of really interesting clients, utilizing a pretty progressive technical stack. So we do a lot of stuff with DevOps, we do a lot of stuff with alternative data stores as well as traditional data stores, so Elasticsearch is one of those. We do a lot of things on the JVM, not necessarily just straight Java programming, with Groovy and Rails and Scala and Sharding and Clojure as well. And then we have a pretty progressive front-end team that focuses on a variety of front-end frameworks as well as we do some mobile development on Android. So how this talk will work, first things first, this presentation is free and open source, so if you go to our GitHub account, there's instructions on how to get this set up locally. If you don't have the USB drive or you don't have it in your downloads. I understand, I just found out right before this presentation, there's exactly one USB drive that will be probably shared between all of us. But there are some instructions that Jonathan back there is passing around and help you guys get set up.
Who's got the USB drive right now? All right, that guy can use it.
Yeah. So we will probably run out of time. I do want to be respectful to the other presenters. And like I said, this is a longer workshop that we've compressed. So really think of it as a best of presentation. We'll try to get through as much of it as we can. This presentation is focused primarily on developers, so we have a lot of content that's focused around system administrators as well. That gets into cluster design, that gets into like security and that sort of thing. So there's a lot of stuff that we probably won't cover. Security, there's some very cool niche features of Elasticsearch like suggestors and more like this queries. We're not going to be talking through language-specific drivers because this is a language-agnostic conference. And so while you can connect to Elasticsearch through Java, you can connect to it through .NET, Python, PHP, whatever framework of choice you want. We're mostly going to be working at the REST API level, just so that you have some familiarity with the vernacular, regardless of what programming background you come from. And we may, at the end, have a hand-wavy demo of the out stack, which is a front end that exposes a bunch of time-based data. And allows you to compose dashboards of reports if you're aggregating logging events from several servers. How many of you, just by show of hands, are familiar with Elasticsearch or have it somewhere in your development or production stack? All right, cool. Oh, okay. I saw some hands go up at the last minute there. So how many of you have used Logstash before or are familiar with that? Okay, so we'll spend just a little bit of time talking about that because a lot of companies are actually using Elasticsearch solely for handling logging events, and it's really good at that. So before I start, I want to give a little bit of background context on Elasticsearch. That very tiny picture on the slide is a man by the name of Shay Bannon. He was the original creator of Elasticsearch, and for the first maybe like 16 to 18 months of the life of the project, the majority of commits to this project were done by him, so 95% of the code. And then from there, it kind of took off and became like this crazy open source thing with many, many different commits a day. And you'll see often throughout Elasticsearch there's a tagline that just says, for search. And now they're actually extending that to say, for logs and, for a bunch of other stuff. But the core focus was search initially. So to set the stage for why we like Elasticsearch and why we adopted it originally in our company, this is a tweet by an industry analyst named Michael Cote. And he tweeted about 4 years ago that for UI UX people, search should be your #1 priority. By show of hands, who's maintaining some sort of business application? And who is in that business application has use cases where people need to find things in a database or in a document store or something like that, right? So oftentimes, search concerns get overlooked. You get situations like this comic here, where at the top you have a very simple search interface, something like Google, where people can just type what it is that they're looking for and find it. And then very commonly with enterprise apps, you have a very complex form where you have to fill in the first name field and the last name field and select a drop down for the state. And I'll give you an example from an insurance client of ours many, many years ago. They had a claims administration application. And the customer service representatives would get a call from a customer on the phone and say something like, hey, I have a Honda Civic 2003, my name is Bill Jones, and it needs service. And as the customer is telling them this information, the CSR is going in and selecting the first name field, typing that in, selecting the last name field, typing that in. going over to the make model, if someone gives the information out of the wrong order, then they have to kind of jump around. And so the average call time just to find a contract is something close to like 45 seconds to a minute. And while all that's happening, the customer is waiting. The customer is frustrated, right? So through the use of search technologies, at the time there was Apache Solr that was kind of the bread and butter. We were able to take that down to something that was much more like a Google search interface where they could just start typing in Bill Jones Honda Civic 2013 all in one field and then find the contract. And our average wait times for contract retrieval went to something like 10 seconds or below. And so we're able to see a lot of advantages with that. And every enterprise that I've seen, there's at least 3 or 4 major use cases like that, where developers may not be realizing that their users are frustrated and that there could be a better experience to look at. So just to talk a little bit, so how many people use relational databases in their day-to-day activity? All right, so most of you. And so you're familiar with kind of the traditional query model. If you don't have full text search enabled capabilities on something like Postgres or Oracle Endeca, you're often writing where clauses that are going against specific fields. And if you need to search across fields, you can accomplish that, but it's a very complicated SQL expression that spans pages, makes the database do a lot of work because it's got to do full table scans against each of those columns. And with Elasticsearch, you can simplify that to just, it has a sensible default that searches across fields and allows you to just quickly retrieve the results that you're looking for. So that bottom example there is just an HTTP request to the REST API. And that's kind of what people expect. The searching across fields thing is also important because a lot of times people don't know exactly where the data lives. And so if I have a document that looks like this, and the red highlighting is a little bit hard to see on the screen, but basically in the name field I have nifty doodad, and in the description I have, this is an example. If someone types an example doodad, they would expect to return the result. But in most cases, they may not, because doodad's at the end of an expression instead of at the beginning of the expression, so you have to do wildcarding on both sides, which is very expensive. And so ideally we want functionality that makes this easy. We also want functionality that makes searches a little bit more humanized. So one example is we probably want case insensitivity. So if I search for iPhone, I'm not really paying attention to whether or not the P is capitalized. I may also be looking for word variations. I could be looking for similar words, so car and automobile. I could be looking at combinations of words being kind of broken up, so show off, and then accents, phone number, patterns, and we're going to show through the API examples some of that later. So before we continue, I do want to talk a little bit about what Elasticsearch is and what Elasticsearch isn't, because some people have kind of some misconceptions about what Elasticsearch is good at. And while it has many strengths, there are also areas where we wouldn't recommend it. So firstly, Elasticsearch is wicked fast. We were in the previous presentation, there was an Apache Bench sort of demo that was given. So we ran Apache Bench against Elasticsearch, and on a simple virtual machine with 1 gig of RAM, we were able to achieve something like 866 requests per second with an average response time of 23 milliseconds against kind of a pretty small database. But it's really designed for that sort of throughput, so you can throw a lot of load at it and it will scale effectively. It's based on Apache Netty, if you're familiar with that. And so most of the I/O operations are asynchronous and non-blocking. It's also highly configurable. So this tiny screenshot is an example of a field analysis chain that we're going to go into a little bit later that allows us to define how data gets indexed and how it gets retrieved. And Elasticsearch has a ton of knobs and sliders to support those sorts of concerns. It's also free and open source. So if we were to go to the GitHub project today, I would imagine that the most recent commit is probably no more than 3 hours ago. It's a highly active project with hundreds of committers from all over the world at this point. I would say next to maybe something like Docker, it's probably one of the most active open source projects in existence right now. It's also distributed and fault tolerant. So this is a screenshot of a plugin called Cough. And what you're seeing here is a number of different Elasticsearch nodes that are all connected together in the cluster, and they're sharing state. So they're sharing the data across the cluster. And so one of the elastic components of Elasticsearch is that you should be able to add new nodes and just scale automatically. If you leave the stock sharding policies alone, if you leave the replication factors as a default, you should be able to get more query throughput, more query or indexing throughput just by adding new nodes to a cluster without a lot of configuration or ceremony. It's also good at handling a lot of data. So the most classic example of that with Elasticsearch is GitHub's code search. Who's used GitHub's code search before? All right, this side of the room, cool. So GitHub is a site that allows people to post, open source or private projects, and they have, quite a lot of data at this point. And so they're indexing 1.3 billion files, 20 terabytes of code, and they have 3.6 million users. And this slide is from like 2 years ago, so it's probably double that now. And what's interesting about the user scenario is that each user has access to slightly different data. And so, Elasticsearch kind of powers GitHub's code search, and it's able to scale that. And we've been working with clusters even larger than GitHub's at this point. So it's really good at that sort of thing. It's also really good not only at structured data, but it's also good at unstructured data as well. So this is an entire Hamlet plate that's been indexed into just one document. So the full body for that, if you're thinking about like Word documents, PDFs, or intranet web pages or something like that, Elasticsearch is really capable of handling that. And even without the structure, you can leverage Elasticsearch's relevance capabilities, which Gary's going to get into, to do a lot to help people find things in this unstructured world. And finally, it's really good at real-time analytics. So if there's time at the end, this is another offering from the Elastic company called Kibana, also free and open source, and allows you to compose visual dashboards of your data. And so this is actually, does anyone remember Star Wars Kid, the viral video from like 2003? All right, it was the first viral video, it was pre-YouTube, and it was just running on some guy's site, right? And so overnight, he started getting millions of hits per day, and he had to scale. And after that whole debacle, he open sources Apache logs. And so in one of our labs, we actually indexed all of those Apache logs into an Elasticsearch cluster, and we're looking at it through Kibana. So we can see, for example, the fact that the majority of the internet in 2003 was using Internet Explorer 6. So very interesting insights that you can gain through tools like that. So now that we've talked about what Elasticsearch is, let's talk a little bit about what Elasticsearch is not. So Elasticsearch is not a relational database, which frankly means that you're not going to be having a good time if you try to do things like join in Elasticsearch. If you expect ACID transactionality, that's also not a great use case for Elasticsearch. It doesn't really have the notions of transactions, so you'll have to do that at the application layer. And what we found to be the most successful pattern if you need those sorts of things is to use Elasticsearch in concert with something like a relational database. So Postgres, or we're also big fans of Neo4j or MongoDB, depending on what your use cases are. It's also not bulletproof. Does anyone know this guy? So this is Kyle Kingsbury. He spoke at a conference here in Chicago a little bit earlier. And what he does basically for a living is pick apart distributed databases. He has these things called Jetson tests, and no distributed database has passed the Jetson test. He's been able to break and cause data loss on Cassandra, on Apache Kafka, on Elasticsearch, on Mongo, on Redis. And so Elasticsearch, most recently, he did an analysis of and found that there are certain areas where if you introduce network partitioning, you can lose up to 90 seconds worth of data. So as an insurance policy, we typically recommend that if you have mission critical data, don't store it in Elasticsearch, store it somewhere else, and then index it into Elasticsearch. So if you encounter some sort of weird network partitioning issue, you can always get that data back by going to your primary system of record. It's also not a web crawler, so a lot of times we'll work with we'll work on projects that are competitive with like the Google search appliance or something like that, where a company wants to index 1 million documents on their intranet. And while the Google search appliance is something that you can drop into your data center and just say, here's where my intranet lives, and it will crawl your intranet and discover the documents, Elasticsearch doesn't have that capability built in. And so if you're looking for that, Apache Nutch is a project that does that really well. Scrappy is a Python-based project that does that really well. Both solutions can feed into Elasticsearch. And most recently, there was a plugin released for Elasticsearch that attempts to do that. We haven't really tested it out in anger, so we don't have an opinion on it yet. It's not a machine learner, so if you want machine learning, how Spark's MLlib or Carrot2 are options depending on what type of machine learning you do. Elasticsearch serves as a great data sync into those sorts of platforms, but you're not going to be able to do a recommendations engine generally with Elasticsearch alone. You're going to need some outboard features to make that happen. It's not a user-facing search experience, so it basically stops at being a REST interface. This is short of Kibana, which is a user-facing search experience for time series data. But if you want a search experience similar to something like Amazon.com, you'll have to do that yourself. And so you would connect to the Elasticsearch REST API, either through your middleware application or directly from the front end, and provide those sorts of user experiences. And finally, it's not secure. So Elasticsearch out the box trusts whoever has access to port 9200. If you have access to port 9200 or 9300, you have keys to the kingdom. You can delete the entire index. You can play around, and in certain cases, there were actually a few people that found ways of executing arbitrary code against the Elasticsearch scripting API. So you'll want to treat Elasticsearch similarly to if you treat the way that you would treat a Postgres database that didn't have a password, and control at the network layer who has access to it. In our longer form talk, we actually go through some security patterns to address that. And Elasticsearch also has a plugin that's available if you like commercial support called Shield that allows role-based authentication through Kerberos and node-to-node encrypted transport as well. So before I move on, are there any questions about what Elasticsearch is and is not? All right. So Jonathan's going to get a little bit into terminology, and hopefully that'll help unpack some of these concepts as we start playing around with the API.
Cool. So we're going to use a lot of this terminology in the remainder of the talk. So we'll want to make sure I'm going to try and make it as clear as possible. And I will be making some analogies to the relational world, and these are more for the ability to sort of bridge the gap and not actually down to the wire. These are not going to be totally similar all the way, but I'll make caveats there as we go. So first of all, we're going to talk about a document. A document in this case is just a JSON object. It's the smallest searchable unit. It's something that you're sending to Elasticsearch to then index. It's self-contained, and you can have documents within documents, much like you can with regular JSON. A document is built using a set of fields. So just like JSON, you have a set of fields, and each field has a value, and it may look something like this. So this is maybe something that you would pass to Elasticsearch, where you have field 0 and its value 777, field 1 and it's got a string value. We have values of lists, and we have this subdocument, so subfield 1, subfield 0, that have values here. Now Elasticsearch is going to take that and decorate it a little bit with some internal things based on which index you're passing this document to, and what type the document is, and an internal ID as well. So that's a document. It's roughly equivalent to like a row in a table if you're into the relational world and familiar with that. Now each key has a value, and so the value can be one of the following data types. So we have regular, like string, integer, long, float. We also have some interesting data types like IP and geopoint and geoshape. So you're actually able to execute queries against Elasticsearch and get results that are just within a certain geoshape. So if you wanted to say, like, I want restaurants that serve burgers, right? The user is typing in burgers, and they want only restaurants within their neighborhood. So you pass in the geoshape of the neighborhood, and then it will limit your results to that, which is really interesting. Now, once you have sort of the idea of what a document looks like, you want to specify that some way. In this case, we're going to call it a mapping type. And a mapping type just tells Elasticsearch what to expect out of a particular type of document. So you want to expect a name, which is going to be a string, maybe like a date created, which is going to be some sort of a timestamp. This is similar to like table definition. And so each document in Elasticsearch will have a mapping type, and so you can get a bunch of similar documents all with the same mapping type, and you can treat those all as one and easily query across it and know what to expect out of that. Then we have this concept of an index. An index is a siloed container for one or more mapping types. So you can sort of think about this like if a mapping type corresponds to like a table definition, and then all of the documents of that mapping type are like a table, then an index is going to be a database. You can have multiple mapping types within an index. So you might have in one of the data sets we're going to examine Divvy. Is everybody familiar with the Divvy bike share system in Chicago? So we have in a single index we have a document type, a mapping type representing rides that were taken, and we have another document mapping type living in the same index representing stations. So you can have as many mapping types in an index as you choose. You can also search across indices if you want, so you can, you're not restricted at this point at the index level. Now, we're just going to continue zooming out here from the document level out. Infrastructurally, we have a node. A node is just a single instance of Elasticsearch, and you can cluster that. One or more nodes can create a cluster, and this is just for distribution of data and workload. And then in terms of the mechanics of setting up a node and setting up a cluster, you're going to split all your indices into shards. So this is just a chunk of an index. And then you're going to distribute those shards across the nodes that you have available. In addition to that, you're going to have replicas of each of those shards, and they're going to be distributed across those nodes. So it may look something like this. So you have an index, that's on the left. Shard 1, 2, 3, 4, and 5 represent what that index gets split up into. And then there's a replica of that set up. And then those shards and those replicas are going to be distributed across the nodes in your cluster. So if you look carefully, you can see that any one of these nodes can go down, and you'll still have at least one copy of every shard in your index. We're not going to go too much into clustering or infrastructural design, as this is more of like a development conference. But that's sort of the full terminology of that. So now we have, in terms of the full text search world, we have a couple different concepts that we want to cover. One is tokens. A token is an individual piece. It sometimes is a word, sometimes it's a part of a word, of a string of text that you're passing to Elasticsearch. So if you take a sentence, for example, the quick brown fox jumped over the lazy dog, and then break on white space, you're going to get these tokens. So the is a token, dog is a token. And we'll talk a little bit more about tokens later. We also have things called character filters. So when there's a certain amount of processing and normalizing you want to do to a string in order to more easily search for it later. So one example of this is like you want to bring everything down to lowercase. So there's no case sensitivity when you're searching. And so lowercase is one of the types of character filters that we want to do. You might also want to filter out punctuation, like exclamation points, for example. You don't necessarily want to have to worry about those when you're searching. So that's another kind of character filter. And this happens when you pass a string in. This happens the first thing that happens is these character filters happen. Then we have tokenizers. Now we saw one example of tokens earlier, where it's just on a word and you're splitting on white space. But we have other methods of tokenizing strings as well. So here is this is a plugin called Inquisitor. This is available in on the single USB drive. Who has that, by the way, right now? Okay, cool. So if anybody wants that, we're going to continue passing around. But you also have access to this in terms of downloading, but it probably won't work right now because of the conference Wi-Fi. Oh yeah, let's see. Yeah. So this is the standard tokenized text. This is what we saw before. It's going to break on white spaces. We can also have it break, so the standard also breaks on like hyphens, for example. There's a couple other tokenizers that are really powerful, like ngram or edge ngram. So ngram is going to break your string up into single letters or pairs of letters, which is really powerful because then you can start searching only part of a word, or you can be in the middle, searching the middle of the word, and it'll still bring up results. We also have other tokenizers for things like path hierarchy. So one of the common use cases for Elasticsearch, in the case of using it with Logstash, is that you're going to get logs back, and sometimes it'll be path hierarchies or IP addresses or email addresses in there. So one of the path hierarchies, so if you're looking at var log, syslog, the standard tokenizer breaks it up a certain way, right? So you have var, you have log, and syslog, so it's splitting up on that slash. But the path hierarchy is going to break it up in a way that is understandable to some other sort of searching application. So you can sort of get the ancestors of a particular path and easily search through that. So those are just a few different types of tokenizers. We also have token filters. So character filter happens. Everything goes on a lowercase. We break things out into tokens. And then we often want to do something with those tokens, either adding or removing or changing their values to make things a little bit more meaningful. So the two common examples of this are stop words and stemmers. Is anybody familiar with either of these? Cool. So in the English language, and in any language, you have words that are really crucial to the semantic of the language, how the language is read and understood. Words like the, to, and, it. These words are super important when you're reading and writing and communicating an idea. But when we're talking about trying to find things, they appear so frequently that we don't actually care. It's just too much noise. So stop words represent all of the, basically a list of really noisy words that we want to eliminate from searching. So in this case, let's see, the stop word analyzer, you see quick, brown, and fox, and it eliminated the, because the is more than likely going to appear in, if not all, very many of the strings that we're indexing. And so it's not actually providing any ability to narrow our results. The other version of this that's pretty common is a stemmer. And a stemmer takes, this is based on a language model. So you have like stemmers in English, and you have different types of stemmers in English and in French and Spanish. Each language has a different stemmer, and sometimes many different stemmers, because it's based on sort of a heuristic approach. You're saying, you know, if you have a word like company, okay, so company is, there's company and companies, and maybe you want somebody to be able to search either of those and get results. So if in your document you mention company, and in somebody's query they're saying companies, like we know that that's basically the same thing. So we want to give them results for that. And so we set up, so there's a set of heuristics that you can follow. In this case, snowball, which is a type of stemmer, is going to take both of these representations of company. For example, it'll say, hey, does a word end in a Y? If so, change that Y to an I instead. And then if a word ends in IES, just drop the ES. And then you have this normalization that happens. It's almost on like a conceptual level. This works also for verbs. So if you were going to say runs and running, it's going to, if you see down here on the snowball, it will actually take the stem of that word, which is going to be really powerful in terms of giving people results that they probably want instead of the exact results. Like if you sort of expect to be able to search company and get results that mention companies back. Now, together these three form analyzers. So you have a character filter piping into a tokenizer, piping into a token filter, and then that's what goes into Elasticsearch. So an example of this is that if we're going to try and send a document to Elasticsearch with a string taking over the search world, the first step may be a character filter. And you can see that the T is lowercase here, and we're dropping all the exclamation points. That's the character filter's job. And then we're going to tokenize it. We're splitting, in this case, on white space and hyphens, so that punctuation gets split there. And then we are doing several token filters to get what we're putting into Elasticsearch. So one thing you might notice is that we've gone from taking to take, and that's a stemmer. That's the stemmer. So if we want to be able to search on take or taking or takes, it will all go to take. We've got the stop word, so the gets dropped from the mix. And then we've also added a synonym token filter here. So this is a really powerful part of Elasticsearch, where if somebody searches for one word and there's another word you know to be semantically similar, then you can add that as well. So we've said world and earth mean about the same thing. So if somebody searches for earth now, this will come back in the result set. Now this analysis chain, this happens both when you're putting documents in and when you're indexing documents into Elasticsearch, and when you're submitting queries against them. So it's the same normalization process that happens on both sides. So when you're indexing this document, you'll see span tree totally awesome presentation gets processed into span tree total awesome present. And that's several things that work there. And when you query against awesome presenters, that also goes to the same analysis chain. So you get awesome and present, and you might have a match here. So next we'll talk about what is in this box. And so I'm just going to do a quick rundown of the box. In this case is the USB drive, which is going to be passed around.
But also available on GitHub.
Also available on GitHub.
So before we start that, does anyone have any questions about anything that we presented? We've got some really cool looking Elastic stickers. Elastic's the company that makes Elasticsearch. They were generous enough to offer stickers, but I'm happy to hand out stickers. Anyone with an interesting question? No one? Yes.
What?
Oh.
Sorry.
Oh, no. I was you can have a sticker. But I was offering stickers to people that have questions about Elasticsearch. Yes, how's it going?
So you mentioned that stop words and stemming are available in other languages also?
Yeah.
Except English?
Yeah, and in fact, the snowball skimmer that we're looking at, there's language models built for French, Spanish, Polish, a lot of the Latin-based languages. When you get to double byte character sets, especially Arabic and Japanese and Chinese and Korean, there's generally commercial skimmers that people have spent years of researching that may drop some variations from Chinese language characters. Elasticsearch offers a pluggable model for that. And so there's a vendor called Symantec, for example, that makes a Chinese language skimmer that's often used in conjunction with that. A lot of that is down at the Lucene level. So Apache Lucene is the Java library that Elasticsearch does a lot of its work on top of. And Gary's going to talk about the internals of that in a minute. And then there are some pluggable stimmers that are also available at the Elasticsearch level. Lucene, by the way, if anyone's worked with Solr before, Lucene is the library that powers Solr as well. So Elasticsearch just adds a bunch of clustering and REST API stuff on top of that. So for those of you that were able to get the VirtualBox up, is anyone up and running with the VirtualBox? It didn't work? Or what's that?
I tried to unzip it. It said that.
Okay, when she's getting the matter.
Yeah, it was an error.
Oh. Oh, it's not. No, that's so we didn't touch it on Windows, and maybe that's it. So I apologize.
Well, it's not working on Mac either right now.
Oh.
Right, so it might be the USB drive.
That might be corrupted. I'm sorry.
Why USB drive?
And it's corrupted.
Yeah.
Yeah. So what we can do, as I mentioned before, if you go to GitHub, well, if you take a business card, we will pass out a link by email to this talk. But you can download it. We have instructions here for doing this at home without the VirtualBox mode. And this we've tried a lot more. I do apologize. This actually speaks to having a single point of failure, single USB drive in this case. That's one of the things we generally try to avoid with Elasticsearch clusters. So everything that's in that lab we're going to be going through live today. So just pretend you're looking at your laptop screen as we're driving through these. I do appreciate everyone's understanding on that. But yes?
Just a quick question. So you talked about things that it's not, one thing that did not come up was real time.
Yes.
So I'm not sure.
So it's near real time. And I assume you might be coming from a Solr background, is that correct? Or
No.
Yeah. So Solr historically had an issue with real-time search. Usually when you get a document in, it takes as much as 5 or 6 seconds to index. Now you can do what's a refresh, which forces through the API that the search segments get populated and something's available for search before the REST API returns a response. With Elasticsearch, they actually focus on real-time from the ground up. So they're using some Lucene 4 features that make that real-time. And in Elasticsearch, it's actually a configurable parameter. So you can set in your cluster and actually at the index level what you want your refresh time to be. So by default, it will wait, whatever documents came in a 1-second window, it will index those all at once and make them available for search. But you can also set that to a much wider value, which we would typically recommend for logging statements. So you can have logs available 10 seconds after they're ingested, or a much lower setting if you really need that fine-grained throughput. With the lower refresh interval, you're basically just making your computer do more work because it's got to re-index things over and over again. But the Lucene file system, and we won't get into the internals of that today, but the Lucene file system is actually very efficient for handling those sorts of things. There is also an aspect of eventual consistency that comes into play between shards and replicas. In Elasticsearch, as Jonathan mentioned, there's the notion of a primary shard, which is where the data gets indexed into, and then a replica, which is basically a backup copy that you can use to facilitate searches. And you control through the Elasticsearch settings whether or not you want queries to be routed through the replicas, or if you only want them in an insurance policy. And if you do have queries routed through the replicas, it gives you greater query throughput, but you're sacrificing consistency potentially in some cases. So depending on what system you're hitting, you may be off by a second or two. Let me pass around the Elastic stickers while I'm thinking about it. Can you hand out those two?
Yeah.
All right. Those two gentlemen right there.
I have one quick question.
Oh yeah.
It's related to multiple language, but can you do multiple language searching as well?
You can. Now, typically, the challenge is that you'll want to do your stemming inside of an index time. And so we typically recommend doing either, if you have explicit metadata about what language a text is written in, storing the data in different fields. So you have, for example, body underscore EN or body underscore IT for Italian. And then you can search across those fields, or you can even, based on the context of the user or some data in the HTTP request, you can route to one field or the other. If you don't have that data, if you don't have the metadata specifying what language something's in, there's a library called, what is it called? Oh man, it's an Apache library, and I'll think of the name in a moment, that has a language detection feature baked in, where you basically hand it a bag of text, and it will, based on what words are there, it will try to guess what language it's in, and then you can decorate your document with that metadata. Tika, Apache Tika is the name of that library. So, just so that we have a context for what we're going to be going over today, we will talk a little bit about what's in this demo environment. And I'll send out an email with instructions on how to do this after the fact. But we have 3 major data sources, and actually a 4th that we decided to add over the weekend. The first is a database of films. So we have 137,000 films from it's a now defunct site called Freebase that basically took a bunch of Wikipedia information and tried to structure it. And so we're going to be doing some queries around that, and that's baked in as one of the indices that we'll be playing around with. As Jonathan mentioned before, Divi, we're kind enough to open source some data about who wrote bytes from where to where. Now, it was completely anonymized, but we found some really insightful pieces of information about, for example, what time of year are people 20 to 30 most likely to ride a bike, or what time of day is the most popular for people that are going downtown. And so we'll be doing some of those types of queries in a later part of the presentation when we get into aggregations. And then to kind of wet our whistle with Elasticsearch, we have a much smaller index that's just a list of locations that are in Chicago that we found in Wikipedia. So I think there's like 98 location documents, so we're going to be doing Gary's going to be doing some full text search around that. And then the waxy.org Star Wars Kid thing is the thing that we'll show for Kibana. Just as a preview of that, this is what that looks like. So for example, if I wanted to see people that were viewing this in Chicago on this week, I would be able to do a full text search at the top. And then I could see specifically like what web browsers they were using, what requests came in, what refers were happening. And this is all powered under the covers just by an Elasticsearch query. And so it's really powerful. It even gives you like geospatial stuff as well. Another example to set the context for some of the search solutions that we can power. This was a pro bono website that we developed for a nonprofit that was organizing a bunch of green initiatives throughout the city of Chicago. And it was a way to connect basically nonprofits with other nonprofits that were doing similar things. So if I'm very interested in beekeeping, for example, I can just type in bee in there and see all of the beekeeping initiatives throughout the city. I'll be able to see it on the map. I'll be able to filter into a specific community. I'll be able to filter into a specific category as well. So if I'm interested in beekeeping initiatives that are also involved in education, I can do that. And you can see the speed of this interaction. That's all just powered by Elasticsearch. The web browser is making direct call to the Elasticsearch API. And because of some of the features that Jonathan was talking about, so if I do bee, I'm able to match that with beekeeper. If I do beekeeping, what's that? Yes, yes, it is. So and that's part of the edge ingram functionality that we were seeing before. And so if we attune this a little bit better, we would be able to drop the word then from an autocomplete. But much like Google, like when you're doing a search with Google, you may not expect the first or second result to come back to match your what you're looking for. You may have to scroll down a little bit. We kind of erred on that side as well. So we try to filter out the noise as much as possible for the user without restricting the search domain too much so that they don't find what they need. And so here, like for example, when I typed in beekeeping, that stemming thing that Jonathan was talking about allows us to match something where the text is beekeeper. And so these are the sorts of applications that you'd be able to develop in your own business when you apply Elasticsearch. And we're going to talk through like how we do that in this presentation. We also have Cough. So Cough is a web admin plugin that basically shows you the state of your cluster. So those 3 indices that I was describing there. Here you can see what Elasticsearch server they're running on, how many shards, how many documents are in each index. You can even do more powerful things like controlling backups and that sort of thing and running basic REST queries through this interface. So that's also available for your exploration. This gets much more interesting when you have large clusters of nodes because then you can see how the data is distributed between each of them. But in the interest of running this all on VirtualBox, we're just doing one Elasticsearch node for today. Sense is another plugin that we're going to be using quite heavily. We've actually hacked Sense to make it easier to show you API examples. And so if you go to GitHub and download it and follow our steps, you'll be able to kind of walk through the REST APIs examples. And there will be links that we'll kind of show in a second that do that. So Jonathan showed you Inquisitor. Marvel is also a plugin that allows you to monitor like how many search requests you had over time, how long it took to index certain documents. It's kind of more of like an administrative interface. And then Kibana was this interface that I showed here, where you can basically build dashboards around your data. So as I mentioned, the Sense plugin, let's actually take a look at that. So if I click this link, you'll notice at the bottom there, if you can read it, there's a little chapter reference. And we've created a bunch of API examples here. And so this chapter reference will tell the web browser which example to load up. So that's not a stock feature in a sense, it was something that we had to kind of build for this session. So our very first HTTP query into Elasticsearch, this is just going against the Elasticsearch REST API, is a get call to the root context. And what we're getting back is just basically some information about the Elasticsearch node that we connected to. So each Elasticsearch node generally has a unique name in the cluster. By default, it picks a name of a Marvel comic book character. There's like thousands of them apparently, and oftentimes we'll do research on what character our node got selected. You also get some meta information about what version number you're running, what cluster it's a part of, and that sort of thing. You can change the cluster name from the default Elasticsearch to something else if you want. And then now we get into the fun part. Let's say that we wanted to index a document. So those of you that are familiar with relational databases, in order to get a document into a database for the first time, you generally have to run a create table statement. You generally have to prepare a schema and set users and that sort of thing. With Elasticsearch, I can just put an HTTP request against a resource. So this is the name of the index, this is the name of the Elasticsearch type, and then this is the ID of the document. This index doesn't exist yet. Look, just to show you there's nothing up my sleeve, I'll do a GET request to this. And you'll see index missing exception, right? So if I put a document against the Elasticsearch REST API and an index doesn't exist, it will create it for me. And it will use sensible defaults to try to guess the mappings of various fields. So let's go ahead and run this. So I get back a response that tells me the index, the type, and ID of the document that I just created. I'll also get back a version number, so you can use multi-version concurrency control. If you're familiar with that model, if I present it again, you'll see that the created value was once true and now it's false because it's just updating a document. You'll also see the version number increment as well. So you can do things like optimistic locking out the box with Elasticsearch, which is a really powerful feature. And we can also retrieve our document through basically hitting the exact same URI, but using a GET request instead of an HTTP put. So for those of you that are familiar with REST, this is kind of old hat, but it's really nice to have this sort of RESTful interface out of the box. Generally, you'll have to write an entire web application that just abstracts from a relational model into a RESTful model, and Elasticsearch gives you that capability on its own. Any questions so far? All right, so moving on. If I want to get back a list of all the documents in this index now, I can do a request to the index, and then there's a special underscore search interface. And by default, if I don't specify any criteria, it's just going to give me back the first 10 results that it finds. It's generally the first 10 results that got indexed, but there's no hard rule around that. It's actually somewhat random. So here I've only created one document, but you'll see that it took 35 seconds to execute that query. Or I'm sorry, 35 milliseconds. Thank God. Okay. It ran the query against 5 shards. So even though there's one document, by default, 5 shards will get issued because Elasticsearch is planning to eventually have data distributed across multiple nodes. So each node, each shard executed the query. 4 of those shards returned no results. 1 shard returned 1 result. And that's the result that we're seeing here. So you get the total number of results back, and then you get an array of hits. By default, you'll get 10 hits back. But the total number tells you how many you need to page through. We'll go through various paging models in a minute as well. And then if we want to review the mappings that Elasticsearch created, so Jonathan went through mappings a little bit, you'll be able to see that based on the shape of the document that I initially submitted, Elasticsearch guessed what some of the types are. Now you don't have to do this dynamic thing, but it's actually pretty powerful. So keywords, I gave the keyword field as a string, so all future keywords now in this index will have to be strings. For the date, you'll notice the date was actually just a string, but what it'll try to do by default is convert that string to a date, and if it converts, then it'll treat that as a date field. We've also got a number in here, so the Wikipedia numeric ID, and it was able to detect that as a long. And so now I have a schema just from a sample document, which is a really, really powerful feature, as long as the schema is relatively homogeneous between documents. This can trip you up sometimes, so the most common use case would be if I index something that has a number value, and then later I try to index a string. Indexing the string in that same field is going to fail. And so in that case, you have to do a migration from one index to another and flipping over the filter alias to point to the new index. That's kind of the pain. We've been working on a solution around that that we're hopefully going to open source at some point. But right now, that's like one of the biggest kind of trip-ups with Elasticsearch. So that takes us through kind of the getting started. Does anyone have any questions on that yet?
So on that theme, would you recommend doing it in a different way if you want to be thoughtful about how you set up your schema?
Yeah, so we have a whole section that we're going to be talking about explicit mapping. What's nice about Elasticsearch is that you can actually use a blend of explicit and dynamic mapping. So if you submit a bunch of documents that don't have a field for the first time, much like Mongo, when you submit a 6 document that has a brand new field, it will create dynamic mappings. Now you can turn that behavior off if you want to be really strict, which isn't a feature of Mongo as far as I'm aware. But that gives you the capability of saying, I really, really want to make sure that this field is a string, that this field is a date, but I've got all this heterogeneous data that I don't really care about in the data bag, and just let Elasticsearch map that however we want. And you can do that through template settings, so index template settings. I don't think we go into that in this lab, but if you shoot me an email, I'll give you a business card, I can send you some examples of that as well. All right, so now we're going to talk a little bit about indexing. So the anatomy of an indexing request is visible on this slide, but I think it's much cooler to do API examples. I don't know about you. So if we want to index, we have 2 options as far as the HTTP verbs that we select. So we showed you before put, where we had an explicit ID as part of the URL, but we can also do a post. So in this case, we only provide the index name and the mapping type, and then we give it a data bag. And then at that point, Elasticsearch will actually assign a unique ID for us. And so you get that back as part of the response. And if I wanted to do a search now against this index that I created, I should get that one result back with the ID. And again, automatic mappings still happen, so I'm still getting that one property type string. As I mentioned before, you'll be able to compose dynamic mappings over time. This is an example of that. So if I wanted to update myself now, so this is the same resource, this is a different resource. I want to add a new field for myself as Cedric. I can do a put against that resource, and I'll get back a new value. And then if I go back to the mapping here, you'll see that there are now 2 fields that are mapped. So you can you don't have to do it all in one shot. You can kind of build it up over time. And then I'll be able to get myself out as well through a GET request to that URI. I can also do updates. So this is kind of a nice feature of Elasticsearch as well. If I wanted to not necessarily overwrite the whole document, but only add a field, I can do that through an underscore update request. And then you can either pass it in a partial document, or you can pass it in a script, which we'll show in a second. So in this case, I'm going to include the number of Git commits that I have. This number has actually gone up probably pretty significantly since we originally prepared this API example. So I've updated myself now, and if I go back, I should be able to see that I've got Git commits in there, but I haven't destroyed all the data that was previously there. Following along so far? Okay. But I could also increment. And so in this case, we talked about some of the security restrictions around dynamic scripting, and we won't get into that here. But in this example, we're basically using the groovy language, and we're able to grab the Git commits directly out of the existing document and increment by 1. So let me run this, and then I'll go back and take a look at my setup. Oh, yeah. I disabled dynamic scripting. Yeah. That doesn't work anymore. Okay, so yes, so this lab was originally written for Elasticsearch 1.3. where dynamic scripting wasn't disabled by default when we upgraded. Now, for security reasons, they no longer let you run dynamic scripting unless you explicitly set that flag. So if that flag were set, I would be able to see that I've incremented my value by 1. Another option that you have is to do a combination of a partial document update if a document exists, or an upsert if a document doesn't exist. Who's familiar with the concept of an upsert? So an upsert is basically saying, I want to create a document if none is already present for this ID. But if the document is not present, we're basically going to generate it with some default value. So in this case, I don't want to override Kevin's name or his title if the document exists. But if the document doesn't exist, then here's my default values for Kevin's name and title. I'll run this. Kevin doesn't exist yet, so I should be getting that back. So let's go ahead and get Kevin. Actually, that would be, okay. So we'll grab that, and then now let's say that we want to create some sort of variation in this payload. So if Kevin exists, I'm going to set his git commits to 1913. If he doesn't exist, I'm going to set it to 1914. So we'll do that, and you'll see the version incremented. So which one do you think won? And we're going to take a break in about 5 minutes and then come back and do the second part. So you'll see now that I'm able to do this. And then finally, one of the really nice features, especially if you're doing like heavy data that's maybe coming over from a primary data store, is the bulk API. So the bulk API allows you to submit multiple documents or multiple document manipulations in one payload. So in this example, I am going to index Gary, and so the first line is actually line delimited JSON. So the first line describes the operation that I'm doing. So I want to do it against Gary, and I'm doing it against the span tree index. And Gary is a type person, so I'm going to create a new resource called Gary. I'm going to pass in the source payload here, and then so you have 2 lines. The first is the operation, the second is the document that you're including as the payload. And then I'm going to do that same process again for Jonathan. So I'm also going to index Jonathan. And so basically you can have like up to, usually we stop around 50,000 operations in a single bulk payload. But you can just kind of strike back and forth operation, payload, over and over again. And do that all in one rest commit. So now we have some people that we've upserted, some people that we've inserted through the post API, some people that we've inserted with an explicit identity through the REST API. And so now I have 5 people. I've got Kevin, I've got Johnny No Name, who was my post request. I've got myself, where I inserted initially and then did some scripted I did some upserts to myself. Gary and Jonathan, who were bulk indexed as well. So any questions on indexing so far? All right. Well, now might be the best time to kind of take a break, and then we'll come back and we'll do querying, which is kind of one of the main purposes of Elasticsearch. So Gary's going to get into some math. Everyone get in your math mode, but there will be cat pictures. So
What time are we coming back?
I think we're going to come back in 10 minutes, so 2:40. And I'll be happy to kind of, if people have questions in the meantime, I'd be happy to kind of answer those. Yes, so it's github.com/, actually let me create a bit. Yeah, I'll do a bit lead.
Actually, that's what I had. I know this.
Correct. Kibana is a front-end interface. And you can use it actually to visualize any sort of data. So it doesn't have to be time series, but 90% of use cases. What's that? It is an alternative to Splunk. There's some things that Splunk does that Kibana actually do. So like complexity processing, you're saying this event happens, but this event doesn't happen, then it's much better. There's some other tools that we work with to do that sort of thing with rules, for example. But just really good it does. Well, so log sections are really cool. There's also sort of a different one in Elasticsearch that can work. Our preference is generally the right customer because every data model is different. So going from a relational model, it's actually one of those. What's your name? Sorry. Oh, yes, yes. Yes, it is. Oh, okay, so pleasure meeting you.
He's on the board, and he has made some stuff up.
Oh, cool. Thank you so much. Yeah, please. Yeah, so I think how are the two sessions? Yeah. Yeah. Would you like to know?
Nice meeting you.
Thank you. Yeah. Yeah, and there's actually two ways. So on the GitHub repository, you can actually go directly to the examples folder, and like it's really here. So we kind of explain what each example is, we explain like what the issue calls, and then we, like I said, we hack sense. So if you follow the links from the slides, or you follow the links from the main, you'll be able to jump in each chapter. So like, if you want to see pagination, you jump in here. You can actually do this request and let's see what actually comes back. So, yeah. Awesome. So I'm so sorry about the virtual docs. We didn't find out about that until like right before. Okay, thank you.
So now, how is it different from Splunk? Because we have Splunk and the house of the company. But I think we are not using it. Yeah, it is only instrumenting the logs. So, how is it different from Splunk and what about the cable?
Yeah, I'm not sure what's on this intro.
I also want to do the hands-on there, so and
Next time we'll do our own.
fresh game. I don't know because of that.
Oh, cool.
You guys want it? You just want it, I can get it.
Yeah,
Because ask for
it's like you're talking about the retail side. How's it going? Oh, yeah.
I can install it.
Yeah.
So you can update maintain.
Yeah. They did, yeah.
Yeah, let's go and check. Yeah, you have like a server.
I'm not that lucky. I didn't get any message.
So,
So
because
far.
it wasn't really designed to do any actions annually. So when you evict the cache, you evict the whole index. Elasticsearch actually stores these caches, like they're mapped to the segment. So if it updates a single segment, it will evict just that cache. But the caches that weren't impacted by the document that got indexed will survive. And so it's much more aggressive in its caching, less aggressive than its eviction. So you have a lot of control. Way better. Especially if you're doing, like, if you have index-heavy applications, that's where activity don't directly use Solar. If you've got very query-heavy applications, there are some advantages to Solar. But, like, the one challenge is, like, Solar Cloud is that it does insurrection. There's limitations on the scale. There isn't really sharply baked into the design. There's a lot of components that should buy from Solar. And so they kind of attach your anomalies with Elasticsearch, and they have skill in my
Track.
Yeah.
You can draw a static image.
Yeah, and that's why Yeah, that's why Logstash got so popular, because that's a very index-heavy application. You probably do 1,000 indexes, index operations. And so in those scenarios, Elasticsearch.
But you know, it's not.
What was your name? I'm sorry. Andy said it. Pleasure to meet you.
Made me want to go there.
Okay, how's it going?
Yeah.
Sometimes you just see
Yes. So not in Elasticsearch, there's no notion of being able to request names from the
you go there and
so I can't go back in time. It's not like a data with a data log where I can go back in time. That's an Elasticsearch 1. The design for Elasticsearch 2, they're planning on adding that capability along with the capability of using continuous query. So you can get change updates in your window, like how to so it allows you to say, like, we're going to run this query, and anytime the document updates that's affected by this query, let me know about it, so you get a stream of updates over time. And that's actually how it does its application. Elasticsearch has a similar capability, respectively. It's not officially there, it's not yet what we talk about. Yeah, but for the moment, like, the versions that are in Elasticsearch are mostly used just to let you know, like, let's say I have 2 threads writing the same document. Thread 1 tries to write, so it has a version of the document, and thread 2 has a version of the document. So right from thread 1 goes in first, and thread 2, yeah, the second one fail. And that's actually an optional measure, so it's not taking the rest of it. But most Elasticsearch clients like JavaScript will take it, will look at the versions for an exception.
or should it just go somewhere else?
Yeah, thank you. Yeah. What? Yeah. Let's see what we got. So I think you can probably skip those scroll queries. Percolator?
It's a super, I mean, we can be,
Yeah.
we can just mention it and go.
Yeah.
You know, that's necessarily really.
Mapping. Yeah. I think we got to show aggregations. I can put down mapping as well. There's a lot of API examples for mapping, because that's where we show like stemming. So I might just say, like, check out the API examples. What points to get so I just created the id for the GitHub. People can access that. I should have got on the dash. That's actually. So we're going to get started again in about 3 minutes. For those of you that just joined, this is kind of like a semi-monolithic talk. So in the first part, we kind of went through the fundamentals of Elasticsearch. I believe it's been recorded, but we have a version of that we recorded in another conference, if not. And so we just left off at indexing, so how to get documents into Elasticsearch. Now we get to show all the fun demo candy parts, so we're going to show you various ways of querying Elasticsearch and some mapping capabilities as well. There was an issue with the USB drive. The zip file that was added was apparently too large for the zip format on this USB, and so unfortunately it doesn't work. However, the entire project is free and open source, so everything that was on this zip drive you can actually set up yourself by going to bitname command tree ES, and that'll take you to the GitHub project. And there are some clear instructions, hopefully some clear instructions. If not, please do a pull request that describe how to launch the Docker environment from the local system. And then it's just a one-liner from there to be able to view all the examples that we're going over. And that's actually how we launch it for our systems as well. So there's also a lot of the API examples that we're going over today are in the dub examples folder, which I'll link to from the root of the project as well. So when we went over the indexing API examples, for instance, there's a markdown file that's reviewed directly on GitHub that shows you all of those interactions and explains what they do. So hopefully that will help. In the meantime, we're just going to kind of go through the API examples ourselves. For those that were taking pictures, this is the URL we captured. So this will take you to the GitHub project. All right. All right, we're going to go ahead and get started again. Hopefully everyone's hydrated. So, I think where we left off, we were talking a little bit about indexing. We went through the update API, the bulk API, and then both the post method where you don't specify an ID for a document and the random one is assigned, and the put method where you specify an explicit ID as part of the URI, and then the document will either get created or replaced at that URI. And next up, Gary's going to talk a little bit about querying, and maybe some math components.
Keep bringing up this math, that's not going to be that much. All right, so before the break, we talked about indexing, or at least Cedric did. And the other major part of what you'll be doing is actually querying, and that's actually where like the fun part happens, because that's where Elasticsearch really shines. As we saw, like in a lot of the other like API examples, the search API is pretty easy to use. In the simplest way of using it, you could just use like a GET request against the search underscore search endpoint off like an index, or off of like, if you could have a search endpoint like right here, so you can specify an index, just search everything at once. That's kind of the simplest way of doing it. And here we're doing basically a search for the term late on the field about. But if you're actually doing queries, you're going to be doing a post against that same search endpoint. And you're going to do like a JSON document, and that JSON document is going to describe what your query looks like. Elasticsearch supports an immense amount of queries, most of which you don't have to know right away. And in fact, the examples I'm going to focus on are really kind of the two types of queries, which if you're just starting out, you should probably be looking at. Sometimes it doesn't quite work the same way. So we're going to talk about query string queries and then Boolean queries. So here's like a really simple example of what a query string query looks like. Here we're doing a query against the Wikipedia locations index. So here we're going to look for the term college in any field. So let's see what happens. Right. So here we have, so by default Elasticsearch will return 10 results unless you specify a different size. But here we actually got 9. You can see that the took section tells you how many milliseconds something took. And then you have like the shards that are recording and so forth, stuff that you don't, they're pretty technical that you don't really care about that much. And then another interesting field is like score. So you'll get like a score back for what's the maximum score of all your query. And then you get a collection of hits, which are the documents, which you've indexed earlier. And these will have some more meta information, like the index they're from and so forth, and then the actual source, which is what you really care about in your application. And so here we have, somewhere in here, something in here mentions college. And there were enough mentions of college for this thing to be scored higher than other documents. So we'll have like a score of 0.68, and then Knox document will probably have a slightly lesser score, and so forth.
So the first example included the word college in the about section, and the name, and also in the description.
Yeah. And then you can get a lot fancier with this. So that query section is actually, let me scroll something more complex, is actually kind of a Boolean operation. And by default, it isn't or, I think we have an and in here. So we can specify kind of an and. So I want both theater and theatra, or however you say it. And we can also specify the fields we're kind of querying against, and the fields we're returning. So these here will be the fields we're like trying to do the query against, and these are the fields we actually want to get back in our result set. So when we do a search here, we'll see that we only get name, keywords, and description back. And all of these contain both, we actually have one document here. And because it's the only document in the index that has theater spelled both ways, so we can actually find. I think, yeah, it's in the keywords is theatra, and then we have theater in these other fields. Right. Now where you would use an actual Boolean query is if you want to maybe have some documents from one set and then not from another set. So here you would use something like a Boolean query, and then you would use the must keyword, which is kind of like saying, I want all the documents that I get back to pass all of these queries, basically. And then there's a must not, which it does what you expect. And not forget to track our time. So here you can basically combine sets of results in various ways to control what you get back and what you don't get back. And there's quite a few of these. And there's also in a Boolean query the idea of a should, where you kind of want something, but you're not sure if you'll get it. So you have the should, and then it'll boost it higher if it passes that should portion of the query. Here we're going to search for, we want theater or theatra or whatever, and we also want something that has the word here in it. And the Chicago Shakespeare Theater comes up again because it kind of matches both of those. But then also in the list we'll have a bunch of other stuff that has theater in it or has pier in it. For example, I think the Big Theater doesn't have pier in it, so it comes up anyways. And so those are kind of the two things that we really want to demo in terms of searching. And the other ones kind of follow similar patterns, like everything's out of a query block, and then you kind of have to read up on the specific cases where you actually want to use them, and it's probably not worth going through all of them. But what's interesting is that when you do these queries, they're really, really, really fast. And they're really, really good at giving you information which is relevant to your query, which is like, how does it do that? I can't do that in a database. How does it work? So I was thinking like, okay, how do I figure this out? And this required a little bit of background in sort of information retrieval. Has anyone ever tried to do like text searching or implement something like that? Yeah, okay, so I'm gonna make a lot of mistakes, don't track me too much.
Don't worry about that.
All right, so, oh, this might be really messed up.
Refresh.
All right, just see.
Oh,
it doesn't really.
resolution. Hold on. Yeah. There we go.
Awesome. Okay. So if you look inside Lucene, which underpins Elasticsearch, one of the cool things it has is a data structure called the inverted index. So whereas, let's say, a relational database might have B-trees or something, what Lucene leverages is a data structure called the inverted index. And the way the inverted index works, here, let me build one up here, right, is for each possible word in all my 3 documents here, I can come up with a sort of table that tells me where it occurs, like which documents it occurs in, and which positions in that document it's in. So, for example, for the word it, I can tell that it's in document 0, and it's at index 1, which is kind of over here, and it's at index 4. And then similarly in document 1, and so forth. So not only does this index tell me where, which words are where, but it also tells me how many times it occurs. So we can actually leverage that information to kind of figure out what is the most relevant terms to your query, or the most relevant documents to your query. So in the most simple example is called the vector space model. And what we do is we turn our documents into kind of vectors in some sort of space. It can be a really, really large space. And then we make a vector to represent the query, which can be like a 1, 1, 1. And then we take all of our document scores in these vectors, and we see how close they are to our actual query. And then we do that by taking an angle between them. So in the vector space model, you have all these kind of vectors like this. So you have, like, let's say you have a 3-word query. And then for each of those words, for each document, you come up with a score. So how similar is my document have something to the word A? How similar is something to the word text? How similar does it have the word query? And you have to kind of come up with a score that is also sort of fair. So you want to sort of weigh the important terms more than sort of the unimportant terms. And one very, very popular algorithm for doing this is called the TF-IDF score. A TF-IDF score kind of has 2 parts. For each term, you weigh how frequently a term occurs in a document. So like how frequently, let's say, A occurs in a document. And then you have the idea of a document frequency, where how often does that term occur in other documents in your corpus, which is what you call a bunch of documents. And then what you do with a document frequency is you kind of do this log thing right here, log of where n is the number of documents that you have over that document frequency, which gives you a number kind of between 0 and 1, I think. Yeah, between 0 and 1. And what happens is, if your document frequency, that is, the amount of documents that, let's say, the word A occurs in, is very high, then you have basically n equals df, and then you have log of 1, which is 0, which causes this score to go down, because all your documents contain that word. So it doesn't matter if some document contains that term.
Can I interject an example? So if you have like a bicycle log, for example, and you search for something like bicycle race, chances are most of your articles contain the word bicycle, but race is a little bit more rare. And so it'll boost documents that have the word race higher than documents that just have the word bicycle. And so it kind of dynamically does relevance based on this model.
Right. So that's a TF-IDF scores. And what you would have is basically, let's say like a vector, or let's say an array of all these scores for your query as it relates to the document. And then what you do for all these vectors is you find kind of the angle between them, or let's say the cosine of an angle. And if you remember your linear algebra, which maybe not everyone's taken, but this is kind of the formula for it, but you don't have to remember it.
It's not what we used at all.
Not everyone's taken linear algebra. Not everyone needs linear algebra.
We'll just search for it.
Yeah, you can just search for it, which is what I do. I'm not going to write those things. So here's an example of how kind of that works. So if we start up with our inverted indexes before, and we do a search, let's say work it harder. If MathJax was working correctly, MathJax is working harder. Let's see. It doesn't load like some numbers for some reason. It's very strange. It also is central. Okay. All right. So this is kind of the TF-IDF scoring in action. Very, very slow action. Just 1 second. All right. So for like, let's say the word work, we can see that it occurs once in document 0, and then it's like kind of inverse document frequency is log of 3 over 1, because it occurs in only one document out of 3. And it sort of works that same way for everything. Interesting case is like, let's say it, where it's kind of common in our document corpus. So this log whatever will be really, really much closer to 0 than the log of 3 over 1. And that score will go down. And you can see, I'll turn off the formula so you can actually see what the numbers would be. And so you take a look at all these in like 3 space, because there's 3 terms. And then you make another vector for work it harder, which would be like a vector 1, 1, 1, because nothing matches work it harder more than itself. So you put that in there. And then you figure out what the angle is between that and all your documents, and that's that. But the gist of it is that the most similar in this case is the 0th document, which is work it harder, make it better, because it contains that term exactly. But because this is kind of a bag of words sort of model, that even if I do work harder it will give me the same similarity. So that's kind of some interesting properties of that scoring algorithm. And that's like the most basic kind of scoring you would learn if you were kind of starting out on information retrieval. But Lucene, being kind of state of the art, it's a lot more complex. So inside of Lucene, you have something called a practical scoring function. And Cedric gets mad at me when I go through this slide, so I'm just going to say it's got a lot of stuff in there to correct for all the flaws that the TF-IDF scoring has in it. And if you ever doubt the fact that this might be going on, Elasticsearch has something called an explain query. So let's say you ever do a query and you're not sure why a certain document is coming up higher than the other documents in the query. What you can do is grab the ID of that document, which will be the Chicago Shakespeare Theater in this case, and then kind of form this kind of query where you hit against the /_explain endpoint. So here I want to know why this Chicago Shakespeare Theater was a top hit, or was a hit, for description for the query Navy, Pier, Place. And those numbers right here are called boosts. So this is when you want to boost certain terms in results.
So Navy is 3 times as
And they're only there just to show you the full thing. But what happens is you get kind of this weird description of the equation that Elasticsearch went through in order to get that score for you. So here you have a description of product of, and then you have a list of stuff, right? And that list is like the coordination factor, which is from the practical scoring function. And then inside of the product you have a sum, and that sum has a bunch of stuff in there. And then you can also, somewhere in here, find the actual boost of stuff. So it's like, let's say that boost of 3 for Navy, that's over here. And then it's got an inverse document frequency of whatever. And then you can, now you guys know what that means. So you can kind of make sense of what's going on and why a certain document might have made it to the top of your result list. And that's really the main point of understanding that stuff. Some more details about scoring. So scoring can be modified via boosting like we saw. So individual terms can be boosted if they're really important to you. You can actually do some linear rewriting of the scoring algorithm. So you can do some scripting to modify the scoring. And you can also, I think, make it pluggable. So you can actually put some of your own stuff in there. One of the cool things is that the Lucene version that comes with the most recent versions of Elasticsearch comes with a more state-of-the-art scoring algorithm called OCopy DM25, which is also a pretty interesting thing to use if you have a lot of long documents and short documents, and it's pretty cool. But now for something completely different. Filtering. Filtering is very different from querying. Querying gives you a bunch of scores for your documents, whereas filtering works a lot more like a where clause in a select statement. That is, it actually removes certain results or filters like that from your result set. Here's kind of my best attempt at describing this visually. Let's say you have a bunch of documents that have, let's say, blue in them or red in them. When you do a query against something like this, you get, well, in theory, you should be getting all the documents back, and then these would have some score, and these would probably have a score of 0. What Elasticsearch would actually do for you is actually cut off here and not return any documents that have a score of 0. But really, you would get basically all the documents in your corpus sorted by score. Now, when you actually do a filter for blue, you get only the documents that have blue. So if I had something like blue-green in here, filtering would not return that. In summary, queries are kind of fuzzy, and they give you scores, and they give you relevance, but they're not quite as efficient as filters. In Elasticsearch, filters can be cached, so everything that passes a filter will be stored in memory, so that when you do that query again, that same filter can be used to filter the results, and it becomes faster and faster as you use it. Whereas queries aren't cached, so every time everything has to be rescored. And that's really the main point. So when you can, you should use filters instead of queries. And here's how filtering works. So you see there's kind of, in that JSON document, there will be a query section and a filter section. So just as we had a query for theater or theatra or whatever, we can also filter for the same terms. And having a collection like this means I want this and this. We got the Shadow Shakespeare thing like that.
I think, so this case it might be the union.
Is it or? Okay.
Yeah, I think that's
kind of confusing.
Yeah.
But it might be an or then, yeah. So you filter basically, but this returns
2 results.
Yeah. All right. Another cool type of filter you can do is actually geodistance filtering. So in our Divi station search, we can actually do a filter where we're not just filtering by terms, but actually a radius around a particular location. I think this is our office, although I don't remember the latitude and longitude by heart. So here we can do a query, and we can actually score this depending on how close, or actually we can filter this depending on how close it is to our office. And you'll notice that these aren't scored, so they're not returned in any particular order. So the actual closest one, I think, is Main Street?
Green and Randolph.
Green and Randolph, yeah. But it's not in any particular order, so you just get everything that falls within that filter map. So that's really how it's different. That there are more query options, which I think Cedric wanted to cover.
I'll just breeze through this in the interest of time. So as you would normally expect, like with most databases, you have the ability to do things like the size, so you can specify the size here. You get back 20 results as opposed to the default 10 results. You can also specify from, so if you want to do pagination kind of the classic way, you can say that you want to start from the 10th position and then return 10 from there. So this is all metadata that you'd be able to attach to your query payload. So here I'm getting a slightly different result back than the first one. But what's really interesting about Elasticsearch is it supports what's called a scan and scroll query. And so how many of you have done like cursors in a database before? It's basically the same idea, right? So how many of you have been on Hacker News, the website? It's a very popular like Reddit or Dig-like website that's specific to like technology news and that sort of thing. It's mostly nerds from Silicon Valley. But what commonly happens is people are posting to it so quickly that by the time you finish reading all the links from the first page and you go to the second page, you'll probably see some of those same links because they've shifted positions on the front page now. And so to avoid that, you can do something like a scroll query, where basically it will remember for a period of time, you tell it how long it needs to remember, the entire result set that you need to return, like at the point that you first issued the query. And then you'll be able to receive the next page, and then the next page, and the next page until you've gone through all the results. And so I'm going to walk through the API for that really quick. This is often, like if you have billions of documents in Elasticsearch and you want to get them all out, this is also the preferred approach to do that as well. So at the top, we have the standard search query string that you see before, but we're specifying the search type as a scan. Can everyone read that in the back? Okay. And then you're also specifying the scroll, so this is how long that lives. If I try to access the next page after 10 minutes, I'll get an error. And then you can also specify the size of each page. So I want 10 results back at a time. And so when I do this initial query, and this payload remains the exact same as before, it's just a JSON query that we're running. So we're getting all of the Wikipedia locations that have the word Chicago in them, and I'm getting back the name and coordinates. So I'll run this, and you'll notice instead of getting results back, I get a JSON payload that gives me a scroll ID. This is the most awkward part of the demo. We're going to copy and paste that scroll ID into the next query here. So now you're going to hit the search/scroll endpoint, and you give it 10 minutes, and that's going to refresh the timeout of the result set. And then this really long string ID, which gives Elasticsearch some clue about the results that it should be returning. And it's basically a sort of hash of the registers of the results that need to be returned back. So I'm going to run this, and I'm going to get my first page of results. Okay. So this is 10 results, and then I have a scroll ID to get the next page of results. So we're going to borrow this string again. And you'll notice that as we continue on, this search string is getting shorter because there's fewer results that need to be returned. And so I'll run this now, and now I'm getting back a separate page. So we keep track of the first result that gets returned. So we have home insurance building. I'm going to go back up to the top. I'm going to paste this again. Typically, this is where actual programs help a lot because you don't have to do this manually. And then now I'm getting Our Lady of Sorrows Basila. And I'll keep going. And now I'm pretty much, once I get this equal sign on the end, that lets me know that this is the last page of results to return. So,
You did the
extra. Thank you. Yeah. Thank you for that. These demo gods are not kind to me right now. Let's see. There we go. Let's try that. All right, that broke something. Imagine that was the last. Yeah, we'll chalk that up to copy paste. But as you see, you can very efficiently retrieve those results. So typically, what you would do if you were building a web-based application with frequently changing data, and you wanted to make sure that you retained a consistent result set with your users, you could either store this in cache and create a smaller register as part of your JSON response, or you could just pass the scroll ID as part of your JSON response, and then just allow the browser to continue passing that most recent scroll ID in to get the next result set. Yeah?
How would you do something like jump to the last page?
So you can't with this model. For that, you would want to use the pagination technique that we showed above. So what you are getting back here is the total number of results. And so you can take that total, know what your last page is, and then jump to that last page by adjusting the front. Okay. All right, so moving on, that's some query options. We also want to talk a little bit about sorting. There's some things about sorting that make sense in Elasticsearch, and then some things that definitely tripped me up when I first started working with it. So we're going to show some examples with that as well. If we're sorting by dates or we're sorting by numbers, sorting works the way that you would expect it to. So here I have the same query that we were looking at before, but I've added this sort parameter here. And so I'm going to sort by the last updated field, which is a date. So let me run that. And you'll see that I get the results back in the order that I would expect. So this is the first entry, if sorted by last date, or last updated, and then you'll see these dates get progressively bigger. If I want to do a descending sort, then I do the same thing, but instead of passing just a string, I pass a JSON object, with the key being the field and the value being the word desk or descending. So I'll run that now, and this is my most recently updated document at the top. And then you'll see the dates go down. You can also sort by distance. So this came up, we worked on a while ago, Chicago.com, which was a gigantic index of all the events that were happening in the city of Chicago at the time. It's not that anymore, sadly. But one of the things that we would often do is show me like the closest jazz concert. And so we would sort all the events based on the distance between where you were and where all these events were happening. We could say, you know, we found a jazz concert happening 0.3 miles from your hotel or something like that. And so to accomplish that, what you end up doing is the same payload that we saw before, but you're going to do a geodistance sort. You pass the geocoordinates, so the latitude, longitude values of your point of interest. So in this case, this is the old Spantry offices. And then you specify you want to sort ascending, so you want the closest positions, and you want it back in a specific unit. So it's smart enough to actually do the geodistance calculations using the Great Circle Distance formula, and it'll give you back values in miles or kilometers or feet or however you want it back. So let's go ahead and run this. What's that?
Qubits.
Qubits. I don't know if that's officially supported, but GitHub accepts pull requests. I think we might do that when we get back to the office. So the old Spantry office, out of the 97 locations that we had indexed in this Elasticsearch index, Skybridge, Chicago, which is where the new Whole Foods is the closest location. And then we have, I think it was a church or something like that. And then we have, I'm not sure what that column is, but I'm really curious to learn. So our office was located, if you know where Girl on the Goat restaurant is on Randolph Street, it used to be on the 3rd floor of that building. And so Skybridge is walkable, so it's doing the right thing in this case. And you can basically use this to return contextual information. In a expanded version of this talk, Gary goes into with suggestors how you can actually use the context to be just a part of the recommendation. So you would be able to adjust the distance as part of this function, but if you have something, if I'm typing in a specific venue name, that may come up first. So you can do kind of blended scoring or blended suggestions based on that. Now let's get into strings. Strings are a very interesting topic when it comes to sort. So let's say that I want to sort by the name of the locations, right? Let me run this query. So this is the same thing as what we had before. We're passing in a field that's mapped as a string. So my first result that came back is Wells Community Academy High School. And then I have Bronzeville Scholastic Institute, then Clemente High School, then Peggy Note Park Nature Museum. Can anyone take a guess as to what's going on with Elasticsearch here? I'll give you a hint, it's right over here. So Elasticsearch does its sorting based on the inverted index. If you remember from Gary's presentation, the inverted index is basically like the back of the book where it tells you what page certain things are on. And so what's happening is because we're tokenizing to build that inverted index, it's going to return the first token. So in this case, the first token that sorts the highest alphabetically is the word academy. And so that's what actually it's sorting Wells Community Academy by. Then we get to Bronzeville Scholastic Institute, is sorting by the token Bronzeville. And then for Clemente, it's sorting by Clemente. And for Peggy Note Park, it's sorting by the museum. But that's not really what we expect. And so to get around that, what we would typically have to do is create a special field that doesn't tokenize on white space and sort on that. And that's exactly what we're about to show next. Any questions on this? Does this make sense? It's a little bit counterintuitive, but it also allows Elasticsearch to sort really quickly without doing scans. In the Wikipedia index, we defined a bunch of mappings. And so let's take a look at the mapping for, we have a special analyzer that's specific to sorted fields. So we have something called sortable here. And if you remember from Jonathan's part of the presentation, we went over filters. This is filters in action. We may actually skip over part of the mapping section. So this is a good time to review it kind of in brief. So what we're doing is every time we have a field value that comes in, the first thing we're doing is we're doing ASCII folding. So let's say that we have something with an accent over the E, that's going to normalize to just the ASCII E. And then we're converting mixed case strings to lowercase. And then we're also removing anything that isn't an alphabetic character or space. So numbers get removed, or punctuation gets removed. And then the most important part here is that we're using a different tokenizer. We're not using the standard tokenizer, we're using what's called the keyword tokenizer, which preserves white space. And now, if we take a look at our mappings, we'll see that we actually have in the name field a bunch of what are called multi-fields that hang off of that. So on the name field specifically, we have a subfield called sortable. So whenever a name comes in, we're analyzing it a few different ways. We're analyzing with the edge integrams, we're analyzing with the sortable analyzer, we're stemming it, so we can query against the stem form if we want, and we're also applying synonyms. So in the case of like building, we may take the abbreviation BLDG and expand that out to a full spelled building. And so now that allows us the flexibility of doing a sort on this subfield. Let's take a look at how if I was indexing something on name.sortable, it would be broken up. Let's start with the actual classic example. So with the standard analyzer here, what you're getting back is the token I want to know what love is. I want you to show me, I think is the full thing. And then if we want to take a look at what we would actually be sorting by now, you'll see that it's just a single token. But we are removing punctuation. We're moving everything to lowercase. There's no ASCII folding to speak of here. But basically, this becomes the fields that we're now sorting on for that token. So now let's go ahead and sort strings the right way. So instead of calling sorting on name, we're going to sort on name.sortable, one of those multi-fields that we just showed. And so now we get the results back in the order that we expect. And you'll see that the string that we're sorting on here now is Bronzeville Scholastic Institute. So it went lowercase. You'll have Clemente High School, and you'll have Peggy No Park and Wells Community High School. And so a lot of times, depending on the context of what you're doing, you may reference one multi-field or another. And Elasticsearch gives you the flexibility to do that. Does anyone have questions on this part? Okay. So I'm going to move on then to the percolator. Fun fact about this slide, who knows what the percolator, the dance from the 90s? No? All right, one person, cool. All right. The fun fact about this slide is that's not actually the percolator. We did a YouTube search for the percolator, and then we asked like the guy that made that song. No one does the percolator. All right, so Jonathan's briefly going to touch on that.
Yeah, so I'm not going to go into too much detail for the sake of time, but I'm just going to sort of amuse your palates on this. Normally when you, the normal flow for Elasticsearch is that you index a document, and then you submit a query against an Elasticsearch index or multiple indices to get the documents that match that query. So percolation is this whole process but backwards. So what you actually end up doing is you index a query, and then you can issue documents against an index and then get back all the queries that match that document. So this is a really great use cases are for when you want to develop some sort of a feed. You have data coming in and you have people interested in a certain type of data that they're going to define into a query. And you log that query, and as new data comes in, you hit the Percolator API and see who is interested in based on the matches that are made.
So like an RSS feed, for example.
Exactly, yeah. So one particular example, like a really great example of this may be in a dating application, for example. You would set, okay, there are a few things I'm looking for in a partner, maybe 4 or 5 things, and if I can find somebody with those attributes, then this is a perfect match for me. So then that's a query, and then you would log that query. Okay, so you're registering this percolator, and then as new people sign up, you use their profiles and then query their profiles against the Percolate API to see whose queries would match, and then you can find perfect matches like this. I'm not going to actually run any of the examples, but I'll show you. So we like T and span tree, and I'm going to cut the story short. But this is the idea of how you might subscribe or to register a percolator. So you're really just sending the full query that you would have to do if you were going to search for something like Earl Grey in a drinks field here. But we're submitting it instead of against a particular index and a particular type. We're specifying against the index span tree and then of this type dot percolator. And then later on, we can hit this Percolate API, which is separate from an indexing API, it's separate from the search API. We have a document here, and then we can submit that and then see what percolation queries that we've registered match that particular document. Where is this slide? So we sort of switched around our intermission here, so sorry, that's just a tease there.
Just do like a little stretch exercise.
Right. So I think we have about 15 minutes left. I think we're going to discuss a few more things, one of which is mapping analysis and embedded objects.
And actually, yes, we have about 15 minutes left. All right. So automatic mapping. So we talked about this in brief, but I just want to show a couple examples of how this would work in practice. So if we need to, let's say that we want to define our own explicit mappings, you do that by posting to the index, and you pass a JSON payload that contains a mappings value. And then for each type, you specify the properties and the fields that are associated with, or the type of analysis you want to apply on those properties. So for example, we can tell Elasticsearch that name is a string, keywords is a string. What's interesting is you can actually pass lists of strings in, even in a string field, and Elasticsearch just does the right thing. But then Wikipedia numeric ID is going to be a long, last update is going to be a long. And then let's say that we run this now, and let's do a bulk index. We're doing a bulk index with some fields that we didn't explicitly define. So if we look at the mappings, it's actually going to be a union of the explicit mappings and the implicit mappings that got generated. So an example of that is geometry type. We didn't specify that in our original mappings, but it just came along for the ride because we had a document that had that field. So another thing we can do is we can specify, let's say that we're going to create a new index with span tree. So in this case, we're indexing the number of dogs that our employees have. So Andrea has 1 dog. And then someone else has a different impression of the schema, and they try to list the names of all their dogs. So this is an example that is going to fail. So I'm creating a list of dogs in that same field, and since I'm passing in a string instead of a number, Elasticsearch is going to fail. So in those sorts of cases, like typically what you'd want to do if you decide that you do want strings, is you use some sort of migration use case, or you could create a separate field called dog_names or something like that, and store the names and make count maybe a scripted property if it's not explicitly defined. Any questions on that? All right. Another thing that you can do, and I'm not going to go into too deep with the detail here, but a common use case is how many people have tried to do phone number search in a relational database? No one? Is it fun? It's not fun, right? Okay. So classic example, I've got phone number in as a kind of old school formatted string with the parentheses and everything, and then someone's trying to search on that phone number with a more modern format, kind of like an IP address style, and I'm getting no hits back. Well, why am I not getting hits back? Let's take a look at the mapping for phone number. So phone number is being mapped as a string, and because I haven't specified any analyzer, just using the standard analyzer. So if I take a look at the mappings for this part of the phone number, you'll see that 312642 and 4600 are broken up as the separate tokens, but then the phone number here is broken up as a single token. So what I really want when I'm doing phone number search is actually just the digits, right? I want to get rid of everything else because that's just noise, that's just punctuation. So what I can do is a regex pattern replace, and I can say anytime I have a non-digit character, that's what that regex expression breaks down to, replace that with an empty string. So I define the filter, and then I define the analyzer that's associated with that, and then I map that to my phone number field. And then when I analyze that phone number field, you'll see that I've basically got all the non-punctuation characters or non-white space characters removed. This phone number will also map to the same thing. So now in this new index, let's go ahead and index the phone number the old way, and I'm going to search for it in the new way, and I get back a result. Now what's interesting about the result that I get back, typically in a relational database, I would scrub that information completely, and what I'm actually storing in the database is the phone number without the formatting. But what we're getting back in this source is the phone number with the formatting. So I can preserve the original thing. If I'm doing highlighting, I can actually highlight the whole value, even though I'm searching on a completely different string. And so that's very flexible. There's a number of other examples. What I can do is I'll give you guys a business card, and then I can send you a link to a longer presentation that we did at a different conference that goes into mappings in a little bit more detail. But we do want to spend just a little bit of time on aggregations with maybe the last 5 or so minutes that we have. Because aggregations, some people use Elasticsearch solely for aggregations, and it's a pretty cool feature.
Yeah, so imagine you pipe a bunch of data into Elasticsearch, you're able to do full text search on it, this is great. You also want to get some higher level analytics about what your data looks like. And we can fit that roughly into 2 types of aggregations, buckets and metrics. Now buckets are going to classify your data into sort of discrete groups. And metrics are going to analyze your data. It's particularly obvious with things like numbers. You can get averages and so on and whatnot with metrics. With buckets, you're usually going to specify a field and then sort of group your documents into fields that exist with those values. So a great example that Cedric pulled up earlier already is in the user interaction here, we have community. Okay, so this is something that you might consider like a faceted search. Well, this is just a bucket in Elasticsearch. So you're telling Elasticsearch to return me all the buckets in the field community. And then it will return to you all these different buckets with how many documents fit into that particular bucket. So for an example of that,
We have to hit refresh.
it loads.
Just hit refresh.
All right, so we're going to do an example on the Divi data set. So this is roughly what a ride looks like. You have a trip duration, a day of week, a gender, and this is roughly what a station looks like. So it's really just got a name, a location, and then a capacity for how many bikes it can hold at one time. So we're going to do this bucketing thing on the field gender. And you'll see what we get back is 3 buckets, undisclosed, male, and female. And they're ordered by document count of the number of Divi rides in this case that fit in that bucket. So immediately you might see that, well, undisclosed is huge. These are the people who are non-members. You're getting like a half-hour pass or a day pass or something like that. Whereas these are members, and you can see right off the bat that the number of rides taken by male Divi members surpass the number of rides by female Divi by almost 4. So you can also specify different types of buckets. So you could say, in one version of this, so far, buckets are very specifically a term, like a string field. But you can also bucket on number fields by specifying a histogram, right? So we're saying, so for example, trip duration. We might want to see all our trip duration, and we want to group trips by, within 5 minutes of each other. So we'll say, I want to see all the trips, the number of trips that took between 0 and 5 minutes, and then between 5 minutes and 10 minutes, and 10 minutes and 15 minutes. And so you're able to do that by specifying this type of query, where we are specifying that we want a trip length field back. And it's going to be of the type histogram on the field trip duration, and the interval is 300 seconds, which is 5 minutes. And so when we get this back, we'll get all these different buckets that represent the number of trips that took 0 to 5 minutes, 5 to 10 minutes, and whatnot. So again, this is in search interfaces, this is where you'll find this quite frequently, where you have a faceted search, and it's really powerful to provide somebody the count that falls into a particular category in this case, and it'll help them creatively narrow down their search results. We also have metrics, and this is the number base, this is statistics on your data. And at the base version, where am I here? Here we are. The statistics, let's take a look at the statistics on our trip duration. Okay, so we get the total count of documents in the trip duration, the minimum trip duration, the maximum trip duration, these are in seconds, average, and a sum of all trip durations. We can also get extended statistics if you want to do like variance or standard deviation or your bounds, standard deviation bounds or whatnot. You can do that. And then percentiles is something that Elasticsearch also supports, and it does it distributed, and it's pretty cool if you're into that sort of thing. So we can see like what the values are at the 25th percentile or the 50th percentile, and these are all configurable. So you could say, like what is at the 7th percentile, and it will tell you. So, like we talked about earlier, using aggregations in terms of faceting is a very powerful user experience, and you'll find that in a lot of places. And this is something we might call a term facet. And it enables these visual filters for users to drill into the results and narrow them down. You can also nest aggregations, which gets to be really powerful. So if, for example, so we have another data set that is, okay, so we have another data set that's the film data set that we were talking about. And so what we might want to do is investigate, let's take the top 10 genres that we have in our data set by the number of documents that match that genre. And then we want to do some further aggregation on that. So let's say we want to take those results in those buckets, sort them by release date, and then limit just to one. And then we have like the first movie in each of these top 10 genres. And so that's what a query like this would look like. So here's where we define the top 10 genres, or we're getting the top 10 buckets for the field genre. And then we're going to have this sub-aggregation here, where we're going to call it top genre hits. And we're going to basically sort all these buckets on the initial release date, ascending, and then we're going to limit by size of 1. And so when we run this query, we will get these buckets, a bunch of buckets. Here's a bucket with the genre of film, so this is super generic. We have other buckets with the genre, or the genre drama. And we will see if we drill into it a little bit. So there's our genre, and the top hits. We actually have, this is the round A garden scene. This is 1888.
It's exactly 2 seconds long.
2 seconds long, 12 frames per second, but 1888, that's pretty good. If you go down, you'll see like fiction and action, 1901, 1903. If we wanted to, instead of doing just the top genres, the top 10 genres, we do like the top 20 genres. We'll actually get some later dates. Let's see if we can find some. Oh, I guess Round A is an indie film. That's interesting.
Independently produced.
Horror, these are still pretty early. So here's a music film, okay? So this is 1923, so this is a little bit later on. You can go pretty far into this, and it's pretty powerful in terms of the types of aggregations and queries that you can do with nested aggregations. You can answer some pretty interesting questions about your data. So that is there anything else I think I should
But you can use these aggregations to, like that Divi data that we were talking about before, this is a visualization that we built in Top E3 that will basically show that off. If you're interested in sort of thing, Kibana is also something to check out, but we managed to look in certain cases as well.
So real quick, just to break this down, this is your bucketing. So we have male and female in this case. In this example, we've eliminated the undisclosed version. So that's one type of bucketing, and then we have this other type of bucketing, which is the histogram, which we're taking, by minute, putting all of the trip durations that were in that minute, and then you're able to check that on the front end.
Cool. Well, we are out of time, and I do want to be courteous to the next speaker. So we will be taking questions in the hallway. Certainly grab a business card or give us one of yours, and we can link you to another form of this presentation where we went into some detail. But like I mentioned as well, we'll have even more detailed instructions in the GitHub project about how to set this up independently and kind of play around with it. There's over 120 API examples that were made available through the system. So thank you everyone for your time. Hopefully this was helpful. By show of hands, was this helpful? Be honest. Okay, cool. All right.